Most people think the biggest challenge in hydrogen is producing it. The reality is far stranger. Hidden behind every major hydrogen project is a problem so extreme that entire industries have been built to solve it. The giant storage sphere in front of you contains hydrogen at approximately minus 253 degrees Celsius. Think about that for a moment. Humanity is intentionally cooling a fuel to temperatures approaching the coldest conditions we can create on Earth. Why? Because hydrogen refuses to cooperate with our infrastructure. Unlike oil, diesel, or natural gas, hydrogen is incredibly light and occupies enormous amounts of space. Left in its normal gaseous form, it becomes difficult to store, difficult to transport, and difficult to move around the world economically. This storage facility is the visible part of a much larger hidden machine. Beneath the pipes, tanks, valves, and cryogenic systems lies one of the most important engineering questions of the 21st century. Can humanity build an energy system around a fuel that must be stored colder than almost anything found in nature? The answer begins here inside a cryogenic world where physics, economics, and infrastructure collide. This is not simply a storage tank. It is the opening chapter in a civilization-scale attempt to move clean energy across continents, oceans, airports, industrial clusters, and global supply chains. The reason engineers freeze hydrogen becomes obvious when we compare volume. On the left side of this image, hydrogen exists as a gas. Notice how much space it occupies. This is hydrogen's hidden weakness. It contains tremendous energy by weight, but very little energy by volume. If we attempted to build a global hydrogen economy using gaseous hydrogen alone, storage tanks would become enormous, transportation costs would rise dramatically, and infrastructure requirements would become overwhelming. Now look to the right side. By cooling hydrogen until it becomes liquid, engineers can reduce its volume by roughly 800 times. The same hydrogen, the same energy, a fraction of the space. Suddenly, shipping becomes practical. Storage becomes practical. Export becomes practical. This single transformation changes the economics of hydrogen more than almost any other technology in the value chain. What you're seeing is not simply refrigeration. You're seeing a strategy to overcome one of hydrogen's biggest physical limitations. Entire liquefaction plants, cryogenic terminals, export hubs, and transportation networks exist because shrinking hydrogen's volume changes everything. Without this transformation, many of the future hydrogen supply chains currently being proposed around the world would struggle to compete. The giant gas cloud on one side and the compact storage vessel on the other tell the story of why liquid hydrogen exists at all. Now we arrive at one of the most mind-blowing numbers in the hydrogen industry. A pleasant day might be 25 degrees Celsius. Antarctica can reach around minus 89 degrees Celsius. Most people already consider that unimaginably cold. Yet liquid hydrogen exists at approximately minus 253 degrees Celsius. To reach that temperature, engineers must remove extraordinary amounts of thermal energy from the hydrogen. The molecular visualization in front of you tells the story. Hydrogen molecules in their gaseous state move rapidly and occupy large volumes. As heat is removed, molecular motion slows. Eventually, the hydrogen condenses into a liquid. This sounds simple in theory, but the reality is one of the most demanding industrial refrigeration processes ever developed. Cryogenic systems must continuously push temperatures lower and lower until hydrogen reaches its liquefaction point. Every degree becomes harder to achieve. Every stage becomes more energy intensive. This is why cryogenic hydrogen infrastructure is so specialized. The challenge is not merely getting cold. The challenge is reaching a temperature so extreme that ordinary industrial equipment, ordinary materials, and ordinary engineering assumptions no longer apply. This is where hydrogen stops behaving like a conventional fuel and starts behaving like one of the most demanding substances in the modern energy system. Most people looking at a liquid hydrogen tank assume they are seeing a giant container. In reality, they are seeing multiple engineering systems working together. The reason this image is called the tank inside the tank is because that is literally what it is. The inner vessel contains liquid hydrogen. The outer shell protects the system from the environment. Between them sits a carefully engineered insulation space designed to slow the relentless movement of heat. Every arrow approaching the tank represents an invisible threat. Heat always moves from warmer regions toward colder regions. Since liquid hydrogen is extraordinarily cold, everything around it becomes a potential source of heat intrusion. The storage vessel therefore becomes a defensive structure. It is less like a container and more like a fortress. Vacuum insulation, structural supports, monitoring systems, pressure controls, and thermal barriers all work together to maintain cryogenic conditions. This is one of the hidden engineering realities rarely shown in hydrogen headlines. The impressive storage sphere visible from a distance is only the surface layer. The real innovation lies inside, where multiple systems cooperate to protect hydrogen from the surrounding world. Without this architecture, large-scale liquid hydrogen storage would simply not be possible. The most important thing happening inside this facility is invisible. Heat is attacking the system 24 hours a day, every minute, every second. The sun introduces heat. The atmosphere introduces heat. The ground introduces heat. Nearby equipment introduces heat. Everything surrounding the tank is warmer than the hydrogen itself. That means the entire facility operates in a constant defensive posture. The multiple insulation layers shown here represent successive lines of defense. The outer shell blocks environmental exposure. Vacuum insulation dramatically reduces heat transfer. Additional thermal barriers help reflect radiation. Sensors monitor conditions continuously. Control systems adjust operations in real time. This image reveals something important about hydrogen infrastructure. Many people imagine energy systems as machines that produce or transport energy. In reality, much of this infrastructure exists simply to stop energy from moving where it shouldn't. The facility is fighting the laws of thermodynamics every hour of every day. And despite all of these protections, heat still finds ways to enter. That reality leads directly to one of the most important economic and engineering challenges facing liquid hydrogen projects worldwide. No cryogenic storage system is perfect. Eventually, some heat gets through. When that happens, a portion of the liquid hydrogen begins turning back into gas. This process is known as boil-off, and it represents one of the defining challenges of liquid hydrogen infrastructure. The vapor rising from the liquid is not a sign of failure, it is a consequence of physics. The challenge is managing it economically. Every kilogram of hydrogen that boils off represents stored energy trying to escape. Operators must recover it, compress it, use it, or reliquefy it. The systems shown beneath the tank reveal the hidden machinery required to accomplish that task. Recovery systems, reliquefaction units, compressors, and control systems all exist because boil-off never completely stops. This is where the conversation moves beyond engineering and into economics. If boil-off becomes excessive, storage costs rise, transportation costs rise, infrastructure costs rise. Suddenly, a technology that looks attractive on paper becomes much harder to deploy at scale. This is classic Rene energy system stress. The challenge isn't simply storing hydrogen, the challenge is preserving value while storing hydrogen. And that battle becomes increasingly important as projects grow larger and supply chains stretch across continents. Now we arrive at the hidden cost most people never see. Freezing hydrogen requires energy, a lot of energy. The liquefaction process shown here follows multiple stages: compression, cooling, expansion, cryogenic refrigeration. Each step removes additional heat. Each step consumes electricity. Each step adds cost. By the time hydrogen reaches minus 253 degrees Celsius, a significant portion of its original energy content may have already been spent. This is where the hydrogen economy faces one of its toughest questions. Is the volume advantage worth the energy penalty? The answer depends entirely on the application. If electricity prices rise, liquefaction becomes more expensive. If utilization falls, infrastructure becomes harder to justify. If operating costs increase, project economics become more challenging. This is where winners and losers begin to separate. The companies that survive are often not the ones with the biggest facilities, but the ones with the cheapest electricity, highest utilization rates, and most efficient operations. This is the competitive edge test. Under favorable conditions, many projects look attractive. Under system stress, only the strongest business models remain viable. At this point, the hydrogen industry faces two very different paths. On one side sits 700 bar compressed hydrogen. On the other sits liquid hydrogen. Both systems solve the same fundamental problem. They reduce volume. They make hydrogen easier to store. They make transportation possible. Yet they approach the challenge from opposite directions. Compressed hydrogen uses pressure. Liquid hydrogen uses temperature. One requires powerful pressure vessels and compressors. The other requires cryogenic refrigeration and thermal protection. Neither system is universally superior. Instead, each occupies a different position within the hydrogen ecosystem. This image is less about technology and more about engineering trade-offs. Every solution carries costs. Every solution carries benefits. The real question is not which technology wins. The real question is which technology wins in a specific environment. Different industries, different transportation systems, and different infrastructure networks may reach entirely different conclusions. This is where liquid hydrogen begins to reveal its strategic advantage. Size matters. For passenger vehicles, compressed hydrogen may be sufficient. For aircraft, ships, export terminals, and large-scale transportation systems, the equation changes. Volume becomes critical. Every cubic meter saved creates value. Aviation cannot carry enormous storage systems indefinitely. Ships moving hydrogen across oceans require maximum energy density. Global trade depends on moving large quantities of energy efficiently. In these environments, liquid hydrogen's complexity may become acceptable because its volume advantage is so significant. The aircraft, cargo vessel, transport systems, and industrial infrastructure shown here represent sectors where liquid hydrogen could play a major role. This does not mean liquid hydrogen replaces every other storage technology. It means liquid hydrogen may dominate applications where space is limited and energy density becomes the defining constraint. That distinction matters because it shifts the conversation from which technology is best to which technology solves the right problem. Now zoom out, much further. Imagine a future hydrogen economy operating at global scale. Renewable energy facilities produce hydrogen. Liquefaction plants convert it into liquid form. Storage terminals hold inventory. Ships move energy between continents. Airports fuel hydrogen-powered aircraft. Industrial clusters consume hydrogen for chemicals, steelmaking, refining, and power generation. The image in front of you is not a prediction. It is a scenario, a possible future built around moving energy efficiently across the world. Whether this future arrives depends on costs, technology improvements, utilization rates, policy decisions, and infrastructure deployment. Yet one thing is already becoming clear. If hydrogen becomes a major global energy carrier, cryogenic infrastructure will sit at the center of that story. The giant storage tanks, liquefaction systems, transfer networks, and transportation hubs will become the hidden machinery connecting energy producers with energy consumers. The future may not belong entirely to liquid hydrogen, but liquid hydrogen could become one of the most important pieces of the puzzle. The journey we've taken through these images reveals a larger truth. Hydrogen is not a single technology. It is an ecosystem. Production, compression, liquefaction, storage, transportation, fuel cells, pipelines, ammonia, industrial applications. Every component connects to every other component. That is why understanding hydrogen requires more than reading headlines. It requires understanding systems. The hidden systems behind storage, the hidden systems behind economics, the hidden systems behind infrastructure. H2 Hub by Renee Energy exists to help professionals, developers, investors, consultants, and engineers navigate that complexity. Because the future hydrogen economy will not be built by hype. It will be built by people who understand how these systems work together under real-world conditions. And as we've seen throughout this investigation, some of the most impressive engineering achievements in the energy industry are happening inside facilities operating at -253 degrees Celsius, quietly solving one of civilization's most difficult energy challenges.